So today I'm going to talk about black holes, and I'm going to do it a little differently. Here is like my research, um, and instead of erasing it and rewriting it, I'm just going to talk about what I already have written. So to form it, it's the same thing as the neutron stars. It goes from hydrogen to helium to carbon to oxygen to silicon to iron. Once it gets to iron, and this is all happening through fusion, all that kind of fun stuff. Once it gets to iron, iron is too dense to fuse into anything else, and therefore the entire star becomes way too dense. And then it collapses in on itself and becomes a supernova. Now here, it can either become a neutron star or a black hole. But what makes it become one or the other? Black holes are for the way more massive stars. When it imploded into this tiny little spot, it was so much mass that it actually distorted space-time way more than it should have. So like, back a while ago when I talked about gravity, I had this little thingy. And you can kind of see that it puts a little dent in there. And if I were to put something much bigger on it, headphones case, it makes a dent, a bigger dent. You can kind of see it there just because this isn't actually like space-time. You can see the dent that it leaves. But with a black hole, it is so dense in such a small area, similar to the neutron stars, it goes to a tiny area, like tens of kilometers, dozens of kilometers, if you want to go that way, but still so much mass that it imploded. And what it does is it basically makes a hole in the fabric of space-time, to where all of the stuff that we know about it doesn't make sense anymore. And what it does to the to stuff around it is pretty crazy. So the matter that is orbiting it, because it has warped space-time and gravity so much, like this thing, when it makes that dent, it's gravity. So since it's basically doing this, that's very intense gravity. So matter, what's happening is it's going really fast around it because it goes close and then just starts to orbit insanely fast. Because, like, if I put a marble here, so we have gravity, and then put a thing here, it instantly goes towards it because it goes to the more dense thing because of how it's warping spacetime. So same with black holes, except a lot more. And the black hole is also spinning, so anything that goes near it is going to join in that spin. So matter goes in this, and it's spinning really fast, and what happens is it starts to heat up to thousands of degrees, and it probably more than that, really hot, to where it, because it's going near the speed of light, and so it's getting really, really hot. And then, but that's with matter. But anything can distort gravity enough to mess with matter, but it also affects light. So light will go around here. Like, you've seen pictures, like the famous picture of the black hole. Oh, I'm not in camera. That it's just like a black thing, the black hole, and then there's orange light, an orange ring around it. That's the light being distorted. That's also why black holes have this like accretion disk. In anything you see about black holes, you're going to see a disk around it. That's actually what we see. We can't see black. We can't see nothingness. The reason we identify them is because of an accretion disk. And that's because light, the gravity is being distorted so much that even light goes around it. Like the thing that normally travels in a straight path, because it goes so fast and travels in a straight path. Here, it's not. It goes around the black hole because of how intense the gravity is, because it's literally like doing that. And then you go over to actual time. So it's distorting gravity, and it's called, this thing is called the fabric of space-time. So what that actually means is, like, space, the fabric of space-time, the space part is gravity. So that's the dent here. But it also affects time. when you are near the black hole, everything around you seems like it's spinning insanely fast because like the black hole is spinning, but everything around you seems like it's going super duper fast just because of how much gravity is distorting space-time. And anybody that's looking up at the black hole? No. Okay, so yeah, it's making it to where everything you seems super slow and everything around you seems super fast. So that's how it's distorting space with matter, distorting space with light, and distorting time. So black holes can do a lot, but like that's just what's happening around it. You see the like any drawing of black holes, like what's actually happening at the edge of this, what is happening with it. That is called the event horizon. We really don't know what's going on there because no one has been able to get past it because, yeah, no one's really tried for obvious reasons. Plus the fact that we don't have spaceships that can go out to a black hole yet. But the reason it's called a black hole is because this event horizon, nothing can get past it. Because to get past it, you would have to be going faster than the speed of light. And light happens to go the speed of light, not faster than it. So light goes into the doesn't get past the event horizon. That's why you have light orbiting it, but not going through the black part. And that's why it appears black, because there's a complete absence of light. So nothing can go faster than the speed of light, so that's why there's this nothingness. And yeah, what's going on inside is called the singularity, and we really have no idea what's going on here. This is completely theoretical, but ideas that we have are that it's infinite density, warping space-time infinitely. That's my terrible drawing of space-time. But yeah. Infinite space-time distortion, infinite density, to where it's breaking the laws of what we know. Basically what's going on here, because also the singularity doesn't have any dimensions. Its dimensions are 0. So it's basically a divide by 0, and that's why we get an error. Like, if you've ever done a calculator thing, you get an error when you divide by 0. And that's why we don't know what's going on here, because it literally makes an error. So we don't know what's going on there. Ideas are that you go inside and you get stretched to the thinness of atoms, but pretty much you're gonna die from the heat first, honestly. But what would happen inside? So there's really two main options that we have, theoretically. These are the two biggest theories of what can happen. First, you're going to be ripped apart by gravity until your atom's thin. And that would be, it would be basically like, you just, until you reach this singularity. And that's mainly with smaller black holes because, like, big thing try to get through small, or normal size thing, but it doesn't have as good of a time. But big hole, whoop, it's fine. But the other option, like I said, would be burning to death, because it's insanely hot due to the matter orbiting at nearly the speed of light. But these things have been around for a long time, and they started from the death of a star. So how do they end? They end due to something called Hawking radiation. And the way that that works is in space, there's something called quantum fluctuation. What we think of as empty space is not actually empty. There's little particles popping up and then hitting each other and deleting themselves. So nothing's like, they're just going, and normally this just makes, if you look up quantum fluctuations and all that kind of stuff, that's the little things you'll see that look like waves in space, time stuff. Anyway, that's quantum fluctuations. But Hawking radiation is when you're near that black hole, like here's the slope of the black hole, and you have the two things, and one goes into the black hole and the other escapes. And what that means is this little dude goes into the black hole, but the other one goes out, whereas both of them were supposed to go in, or just not exist. So matter is actually escaping from the black hole, and so it's slowly, very, very slowly, losing its matter. And, like, by slowly, these black holes, some normal ones have a lifetime of 10 to the 10, which, that's a lot. Like, 10 to the 10 billion years, I think. Like, it's a long time. And for after trillions of years, I can't remember how many zeros were after it, but after multiple trillions of years, there would only be less than 1% gone. That's how slow Hawking radiation is. We'll all be dead. All the other stars will be dead. Everything will be dead by the time black holes start dying. They are going to be the last things left. Like, here's the start of the universe. That little line's us. This is when they're gonna die. That's a long time. But that's pretty much the basic stuff about black holes. But there's always more. The information paradox is what makes black holes really freaking spooky, especially for any person that's trying to do science or math in the modern world. So what is information? Information is what gives a thing its properties. So like, we have carbon, and carbon can be coal, but if it's rearranged, it can be a diamond. And then you can have a banana if it's more complex, but you rearrange those same atoms and you get a squirrel. So yeah, information is what makes a thing a thing. It gives a job to the atoms, per se. So a rule of quantum physics and just general physics, everything, is that information cannot be lost, because if we lose like what gives everything its thing, it doesn't make sense. It would break down the laws of everything we know. Black holes, being the lovely things that they are, destroy information. Now, we don't know this, but it pretty much looks like it, because if your warp were in space-time, like these, what happens to the stuff that goes down, away from everything? And really, there's a bunch of theories about it, but if information is actually destroyed down here, like, if it's just gone, then that means everything that we know about physics, all of the rules and laws that we have for the universe, are wrong. So, that's really fun. So that's what a lot of astronomers, physicists, and all that stuff they are working on now. But yeah, that